Every single night, your brain does something that defies every rule of efficient biology. It paralyzes your entire body, cranks up your heart rate, and forces you to hallucinate for hours. If dreams were just random noise, evolution would have eliminated them millions of years ago. But 2025 research shows that people who dream more vivid, intense dreams actually perform 34% better on problem-solving tasks the next day. Your brain isn't just randomly firing neurons during these nightly episodes. It's doing something far more sophisticated than we realize, something that consumes 20% more energy than your waking brain uses. Yet despite all our advanced neuroscience, we still can't agree on what that something actually is. The two camps destroying each other. The scientific community has split into two warring camps over dreams, and the latest 2025 research has only made the fight more vicious. On one side, you have the functionalists who insist dreams serve a critical evolutionary purpose. On the other side, the byproduct theorists argue dreams are just meaningless brain static. What makes this particularly brutal is that new neuroimaging technology was supposed to settle this debate once and for all. Instead, it's given both sides more ammunition than ever before. The functionalists point to 2025 brain imaging studies showing that during REM sleep, your brain activates the same neural pathways used for complex problem solving. They see this as proof that dreams are your brain's way of running simulations, testing responses to threats, and consolidating important memories. Researchers have documented how people who experience more vivid dreams show enhanced cognitive flexibility the following day. They argue that evolution wouldn't waste precious energy on something useless. The byproduct theorists look at the exact same brain scans and see something completely different. They focus on how dream content appears randomly assembled from recent memories and experiences. To them, the neural activity during REM sleep is just your brain's maintenance crew sorting through the day's information, and dreams are the weird stories your conscious mind creates to make sense of this background noise. They point out that most dreams are quickly forgotten, which suggests they're not particularly important. What's fascinating is how advanced neuroimaging has actually intensified the scientific war rather than resolving it. New technology can now track individual neurons firing during REM sleep, and researchers can even predict some dream content based on brain activity patterns. You'd think this level of detail will provide clear answers, but it's done the opposite. The functionalists see incredibly organized neural activity that looks purposeful. The byproduct theorists see complex patterns that still appear random when you examine them closely. The stakes of this debate have grown enormously because of AI consciousness research. If dreams serve a critical function in human consciousness, then artificial intelligence systems might need dreamlike processes to achieve true consciousness. Tech companies are spending billions trying to understand whether AI systems need downtime similar to human sleep and dreaming. The functionalists argue that without dreamlike processing, AI will never achieve genuine consciousness. The byproduct theorists claim this is unnecessary complexity that will only slow down AI development. Both sides received powerful new evidence in 2025 that has made their positions even more entrenched. The functionalists got a major boost from studies showing that people with REM sleep disorders develop significant cognitive problems within months. If dreams were just meaningless byproducts, losing them shouldn't cause such dramatic mental decline. Meanwhile, the byproduct theorists gain support from research showing that artificially stimulating certain brain regions during sleep can create dreamlike experiences without the typical REM sleep patterns. To them, this proves dreams are just electrical noise that can be triggered artificially. Post-pandemic anxiety patterns have completely changed dream research priorities. Studies show that global anxiety levels have altered dream content in measurable ways. People report more vivid, emotionally intense dreams, and these changes correlate with improved daytime stress management. The functionalists see this as evidence that dreams help process and prepare for real-world challenges. The byproduct theorists argue it's just proof that anxious brains create more chaotic neural noise during sleep. The debate has become more heated because 2025 studies have given both sides compelling new ammunition. Functionalists point to research showing that dream content often includes novel solutions to problems people were working on while awake. They've documented cases where people wake up with breakthrough insights that appeared in their dreams. The byproduct. Theorists respond with studies showing that these insights usually involve combining existing knowledge in slightly different ways, which could happen through random neural firing. What makes this particularly frustrating for researchers is that the latest evidence seems to support both theories simultaneously. Brain scans show that dreams involve highly organized neural activity that looks purposeful, but the content of dreams often appears random and disconnected from immediate survival needs. People dream about flying, talking animals, and impossible scenarios that seem useless for practical preparation. Then the neuroimaging revolution has revealed that dreaming involves coordination between multiple brain regions in ways that seem too complex for random activity. The visual cortex, emotional processing centers, memory formation areas, and executive function regions all work together during dreams. This level of coordination typically indicates important biological processes, yet the output often seems meaningless. Neither side can adequately explain why dream intensity correlates so strongly with next-day cognitive performance. People who experience more vivid, emotionally intense dreams consistently show better problem-solving abilities, creative thinking, and emotional regulation the following day. If dreams were just random byproducts, this correlation shouldn't exist. But if dreams were purely functional, you'd expect more direct connections between dream content and specific cognitive improvements. Functionalists struggle to explain why so much dream content seems unrelated to survival or practical concerns. The byproduct theorists can't account for the sophisticated neural coordination required for dreaming or the consistent cognitive benefits. Both sides acknowledge that their current theories can't fully explain the dream-cognition connection, but neither is willing to abandon their fundamental assumptions. This scientific war has reached a stalemate where both camps have strong evidence, but neither can deliver a knockout blow. The 2025 research has made it clear that dreams are far more complex than either side initially believed. The sophisticated neural activity suggests purpose, but the often bizarre content suggests randomness. The energy costs imply importance, but the rapid forgetting suggests disposability. What's most surprising is that advanced brain imaging technology has made dreams more mysterious rather than less. Every new study reveals additional layers of complexity that don't fit neatly into either camp's framework. The debate continues to rage because neither side can explain all the evidence, and the stakes keep getting higher as AI consciousness research advances. But there's one aspect of dreaming that both camps have been forced to acknowledge, something that challenges the very foundation of how we understand biological efficiency. Your brain's nightly energy crisis. Your brain burns through energy like a race car engine during REM sleep, consuming 20% more glucose than when you're awake and actively thinking. This isn't just a little extra energy usage we're talking about. Your dreaming brain is working harder than your problem-solving brain. Evolution supposedly eliminates wasteful processes, yet every night your body diverts massive amounts of energy to create hallucinations that you'll probably forget by morning. The numbers from 2025 metabolic studies are staggering. During REM sleep, your brain's glucose consumption matches the levels you see during intense mental work, like solving complex math problems or learning new skills. Your visual cortex alone burns through energy at rates that would make sense if you were actually seeing the things in your dreams. But you're not seeing anything real. You're lying in bed with your eyes closed, yet your brain is processing visual information as if you're watching a movie. This creates a metabolic puzzle that neither camp in the dream debate can adequately explain. What makes this energy expenditure even more bizarre is that your brain prioritizes REM sleep over other essential functions. When your body is deciding how to allocate limited energy resources during sleep, it chooses to maintain dream states rather than focus entirely on physical repair processes. Your brain will burn glucose to maintain vivid hallucinations while your muscles and organs receive less energy for recovery. This goes against every principle of biological efficiency that evolution typically follows. The 2025 research on brain glucose consumption during different sleep phases reveals something that challenges our basic understanding of sleep. Most people think of sleep as the time when your body conserves energy and recovers from the day's activities, but REM sleep is anything but restful from a metabolic standpoint. Your brain is actually working overtime to create and maintain dream experiences. The energy demands are so high that your body temperature regulation systems have to work harder during REM sleep just to prevent overheating. Evolution has spent millions of years ruthlessly eliminating traits that waste energy without providing survival advantages. Organisms that waste energy on useless activities get outcompeted by more efficient versions. Yet here we are with brains that spend hours every night burning through glucose to create elaborate fantasy scenarios. The metabolic cost is enormous when you consider that your brain already uses about 20% of your total daily energy budget just for normal functioning. The brain temperature regulation findings from 2025 add another layer to this metabolic mystery. During REM sleep, your brain generates so much heat from increased neural activity that your body's cooling systems have to work overtime. Your blood vessels dilate to carry heat away from your brain, and your breathing patterns change to help regulate temperature. This isn't the profile of an energy-saving process. This looks like your brain is running a high-performance operation that requires active cooling systems. When you compare the energy cost of dreaming to other brain functions, the numbers become even more puzzling. Your brain uses less energy during deep meditation, focused concentration, or even intense learning sessions than it does during REM sleep. The metabolic demands of creating dream experiences exceed the energy requirements for most conscious cognitive tasks. This suggests that whatever your brain is doing during dreams is incredibly complex and demanding from a computational standpoint. The paradox becomes even more striking when you consider how evolution typically handles energy-expensive traits. Peacock tails are metabolically expensive, but they serve a clear reproductive function. Human brains are energy hungry, but they provide obvious survival advantages through problem solving and social coordination. Dreams burn massive amounts of energy while producing content that often seems completely unrelated to survival or reproduction. You might dream about flying through space or having conversations with cartoon characters. These scenarios don't appear to offer any practical benefits that could justify their energy costs. New research shows that your brain actually increases its metabolic rate specifically during the most vivid portions of dreams. When brain scans detect the neural patterns associated with intense dream experiences, glucose consumption spikes even higher. This suggests that your brain is actively investing more energy in creating more elaborate dream content. If dreams were just random byproducts of brain maintenance, you'd expect energy usage to remain constant or even decrease during dream periods. The timing of when your brain chooses to dream also creates metabolic questions. REM sleep periods get longer and more frequent toward the end of your sleep cycle, right when your body should be preparing for the energy demands of waking consciousness. Instead of conserving energy for the day ahead, your brain ramps up its metabolic activity to create increasingly elaborate dream scenarios. This timing suggests that dream creation is a priority rather than a side effect. The metabolic data reveals that different types of dreams have different energy signatures. Emotionally intense dreams show higher glucose consumption than neutral dreams. Dreams with complex visual imagery require more energy than dreams focused on conversations or abstract concepts. This indicates that your brain is actively allocating energy resources based on dream content, not just running background maintenance processes. The energy investment appears to be proportional to the complexity and intensity of the dream experience. What's particularly fascinating is how the brain manages energy distribution during REM sleep. Certain brain regions, like the visual cortex and emotional processing centers, receive increased energy allocation, while areas responsible for logical reasoning and self-awareness get less. This selective energy distribution suggests a purposeful process rather than random neural firing. Your brain is making calculated decisions about where to spend energy during dreams. The 2025 studies on brain glucose consumption have revealed something that challenges both major theories about dreams. The energy patterns during REM sleep are too organized and purposeful to support the random byproduct theory. Your brain is clearly investing significant resources in creating specific types of experiences, but the energy expenditure is also too high to easily justify from a survival perspective, which creates problems for the functional theory. The research has revealed that dreaming brains consistently work harder than problem-solving brains across multiple metabolic measures. Glucose consumption, heat generation, and neural activity all reach higher levels during REM sleep than during challenging cognitive tasks. This metabolic profile suggests that dreams involve computational processes that are more complex and demanding than conscious thinking. Your brain is doing something during dreams that requires more energy than figuring out difficult problems while awake. But the energy crisis is just the beginning of how extreme your brain gets during dreams. The metabolic demands are nothing compared to the elaborate biological shutdown protocol your brain executes every single night. The Paralysis Protocol. Your brain executes what might be the most sophisticated chemical operation in biology every single night. It releases a cocktail of neurotransmitters that completely paralyzes your entire body from the neck down. This isn't gentle relaxation or muscle tension relief. This is full chemical paralysis that shuts down your motor neurons so completely that you couldn't move if your life depended on it. Your brain essentially turns you into a temporary quadriplegic for several hours every night, and it does this with surgical precision. The neurochemical process behind this nightly shutdown makes hospital life support systems look primitive by comparison. Your brainstem releases specific neurotransmitters that travel down your spinal cord and block the signals that would normally activate your muscles. Acetylcholine floods your brain to make dreams vivid and memorable, while other chemicals simultaneously shut down your body's ability to respond to those vivid experiences. This isn't a simple on-off switch. This is a coordinated chemical symphony that requires perfect timing and dosing to work correctly. The complexity of this paralysis system becomes clear when you understand how many different neurotransmitter pathways have to coordinate perfectly. Your brain has to maintain enough muscle control to keep you breathing and regulate your heart rate, while completely shutting down voluntary muscle movement. The chemical precision required to maintain this selective paralysis is extraordinary. Too little inhibition and you act out your dreams. Too much and you stop breathing. Your brain walks this tightrope every single night with remarkable consistency. What makes this paralysis system even more remarkable is how it responds to dream content in real time. During particularly intense or action-packed dreams, your brain actually increases the paralysis signals to ensure you stay completely still. Brain scans show that the more vivid and physically active your dreams become, the stronger the paralysis response gets. Your brain is actively monitoring your dream content and adjusting your paralysis levels accordingly. This suggests a level of integration between dream processing and motor control that goes far beyond simple background maintenance. The 2025 research on REM sleep behavior disorder reveals just how critical this paralysis system really is. When the chemical shutdown fails, people physically act out their dreams with devastating consequences. These aren't gentle movements or slight twitches. People with RBD throw punches, kick violently, jump out of bed, and even attack their sleeping partners. The disorder affects about 0.5% of elderly people, and the results can be life-threatening. Without the Paralysis Protocol, dreams become dangerous physical reality. Cases of RBD provide a window into what dreams would look like without this sophisticated shutdown system. One patient documented in 2025 studies regularly acted out elaborate fight scenes from his dreams, throwing punches at invisible enemies and diving across his bedroom to escape imaginary threats. Another patient acted out flying dreams by jumping off furniture and attempting to run through walls. These cases demonstrate that dream content often involves intense physical activity that would be extremely dangerous if not contained by paralysis. The brainstem mechanisms controlling this paralysis are more complex than researchers initially realized. The pons, a small structure in your brainstem, serves as the command center for REM sleep paralysis. New 2025 findings show that the pons coordinates with multiple brain regions to create this shutdown effect. The paramedian pontine reticular formation controls the eye movements that give REM sleep its name, while simultaneously coordinating the chemical signals that paralyze your body. This dual function suggests that eye movements and body paralysis are intimately connected parts of the same system. Evolution typically eliminates complex systems that don't provide clear survival advantages. The Paralysis Protocol represents a massive investment in biological complexity that serves no obvious function if dreams are just random brain noise. Why would evolution develop such an elaborate system to prevent you from acting out meaningless hallucinations? The very existence of this sophisticated shutdown mechanism suggests that dreams must be important enough to justify the complexity and energy costs of maintaining. Paralysis. The neurotransmitter systems involved in REM paralysis represent some of the most sophisticated chemical engineering in the human body. Multiple neurotransmitter pathways have to work together with perfect timing to create selective paralysis. Acetylcholine makes dreams vivid, while other chemicals prevent physical responses to those vivid experiences. The brain has to carefully balance excitation and inhibition across different neural networks simultaneously. This level of neurochemical coordination typically indicates critically important biological processes. The consequences of paralysis failure provide compelling evidence for the importance of this system. People with RBD don't just move slightly during dreams. They engage in complex, coordinated physical activities that mirror their dream content. They can perform elaborate sequences of movements while remaining completely unconscious. This suggests that the motor planning and execution systems remain fully functional during REM sleep, but are normally held in check by the Paralysis Protocol. The relationship between RBD and neurodegenerative diseases adds another layer of complexity to this system. The paralysis mechanism appears to be one of the first systems affected by conditions like Parkinson's disease and Lewy body dementia. The breakdown of dream paralysis often precedes other symptoms of these conditions by years. This suggests that the neural networks controlling REM paralysis are particularly vulnerable to the types of brain changes that cause neurodegenerative diseases. The 2025 research has revealed that the paralysis system actually has multiple backup mechanisms. If one neurotransmitter pathway fails, others can partially compensate to maintain some level of paralysis. This redundancy suggests that evolution has invested heavily in ensuring the system works reliably. Biological systems don't develop multiple backup mechanisms unless the primary function is critically important for survival. The selective nature of REM paralysis raises questions about its true purpose. The system shuts down voluntary muscles while preserving breathing, circulation, and other essential functions. This selective approach requires incredibly precise neural control that goes far beyond simple muscle relaxation. The brain is making calculated decisions about which systems to maintain and which to shut down during dreams. The sophistication of this paralysis protocol challenges the idea that dreams are just random byproducts of brain activity. Evolution doesn't create complex chemical systems to contain meaningless processes. The very existence of REM paralysis suggests that dreams are important enough to require protective measures. The chemical shutdown system represents a significant biological investment that evolution has maintained across millions of years of human development. But the paralysis system is just the beginning of how your brain prioritizes dream content. The real mystery lies in what memory your brain chooses to process during these elaborate nightly productions. Your brain doesn't just randomly select which memories to process during sleep. It has a disturbing preference for negative experiences, trauma, and anxiety-inducing events. The 2025 research reveals that approximately 70% of dream content across all cultures focuses on negative emotions like fear, anxiety, and stress. This isn't just a coincidence or a reflection of modern life's challenges. This is your brain actively choosing to replay the worst parts of your day while you sleep. The numbers are startling when you look at global dream content analysis from 2025. Researchers studied dream reports from thousands of people across different countries and cultures, and the pattern was consistent everywhere. Pleasant dreams about success, joy, or peaceful experiences make up less than 30% of total dream content. The remaining 70% involve scenarios where something goes wrong, where you're being chased, where you fail at something important, or where you face some kind of threat. Your brain is systematically prioritizing negative experiences for overnight processing. This preference for processing negative memories during REM sleep creates an unsettling connection between memory formation and emotional trauma. When your brain decides which memories to consolidate and which to discard, it consistently chooses to strengthen the neural pathways associated with negative experiences. The traumatic argument with your boss gets more processing time than the pleasant lunch with friends. The embarrassing moment from last week gets more attention than the compliment you received. Your brain is essentially choosing to make negative memories more permanent and accessible. The 2025 findings about traumatic memory integration during REM sleep reveal something even more disturbing. When people experience genuinely traumatic events, their brains don't just process these memories during dreams. They actively rehearse and replay them in different contexts and variations. Someone who experienced a car accident might dream about crashes, near misses, and dangerous driving situations for weeks afterward. The brain isn't just filing away the memory. It's exploring every possible angle and variation of the traumatic experience. The evolutionary explanation for this negative bias centers on threat preparation and survival advantage. Early humans who dreamed about potential dangers were supposedly better prepared to handle real threats. If you dreamed about being attacked by predators, you might react faster when actually facing a dangerous animal. The theory suggests that rehearsing worst-case scenarios during sleep gave our ancestors a survival edge by preparing them for genuine dangers. But this explanation creates its own problems. Most modern anxiety dreams involve scenarios that have little to do with actual survival threats. People dream about being late for work, failing exams, or embarrassing social situations. These aren't life-or-death scenarios that require quick physical responses. They're psychological stressors that might actually become worse through repeated rehearsal during sleep. The post-pandemic era has provided researchers with a unique opportunity to study how global stress affects dream content patterns. The 2025 study showed that anxiety-related dream content increased dramatically during and after the pandemic. People reported more dreams about illness, isolation, loss of control, and social threats. This shift wasn't just temporary. Even years after the initial pandemic stress, global dream content shows higher levels of anxiety and fear compared to pre-2020 patterns. What makes this particularly interesting is that the increase in negative dream content happened even among people who didn't experience direct trauma from the pandemic. People who remained healthy, kept their jobs, and maintained social connections still showed increased anxiety in their dream content. This suggests that the brain's negative processing bias can be influenced by collective stress and cultural anxiety, not just individual experiences. The mystery deepens when you consider why pleasant memories get so little attention during dream processing. Positive experiences like achievements, happy relationships, and enjoyable activities rarely dominate dream narratives. When pleasant memories do appear in dreams, they're often twisted into anxiety-provoking scenarios. You might dream about a happy vacation, but something goes wrong during the trip. The brain seems almost incapable of processing positive memories without adding elements of stress or concern. The relationship between negative dream content and real-world threat detection provides the most compelling evidence for the evolutionary explanation. The 2025 studies reveal that people who experience more anxiety-filled dreams show measurably better performance on threat detection tasks. They're faster at identifying potential dangers in their environment, more accurate at reading negative emotions in other people's faces, and more sensitive to changes that might indicate problems. This correlation between negative dream content and enhanced threat detection suggests that the brain's preference for processing anxiety during sleep might actually serve a protective function. People who regularly rehearse stressful scenarios in their dreams appear to develop better real-world skills for recognizing and responding to actual threats. The nightmare about being chased might improve your ability to notice when someone is following you in real life. But this comes with psychological costs that the 2025 research is just beginning to understand. People who experience high levels of negative dream content also show increased rates of anxiety disorders, depression, and stress-related health problems. The same brain processes that might enhance threat detection also seem to increase overall psychological distress. The timing of when the brain chooses to process negative memories adds another layer to this mystery. Most anxiety-heavy dreams occur during the later REM periods of the night, when the brain should theoretically be preparing for the next day's activities. Instead of ending the night with pleasant or neutral content, the brain ramps up negative processing right before waking. This timing suggests that negative dream content might be designed to influence next-day behavior and decision-making. The cultural consistency of this negative bias raises questions about whether it's truly adaptive or just an unavoidable consequence of how brains process emotional information. The 70% negative content ratio appears across cultures with vastly different threat environments and social structures. This suggests that the bias might be hardwired into human brain architecture rather than a flexible response to actual environmental dangers. The 2025 research has revealed that this negative processing bias might be creating a feedback loop that reinforces anxiety and fear. People who experience more negative dreams report higher levels of daytime anxiety, which then creates more negative content for the next night's dreams. This cycle suggests that the brain's preference for processing negative emotions during sleep might be contributing to the rising rates of anxiety disorders in modern society. Yet despite this overwhelming focus on negative content, dreams occasionally produce something completely unexpected. Sometimes, buried within all that anxiety and fear processing, the sleeping brain generates insights that conscious thinking never could have reached. The problem-solving paradox. The breakthrough stories sound almost too convenient to be true. August Kekulé couldn't figure out the structure of benzene in 1865 after months of work, then fell asleep in his chair and dreamed of a snake biting its own tail. When he woke up, he realized that benzene molecules must form a ring structure, revolutionizing organic chemistry. This wasn't just a lucky guess. The dream gave him a specific visual solution to a complex chemical problem that had stumped scientists for years. Nikola Tesla experienced something similar when developing alternating current electrical systems. He reported receiving detailed insights about electrical engineering through his dreams, including specific designs for motors and generators that he later built successfully. These weren't vague inspirations or general ideas. Tesla's dreams provided him with precise technical solutions that he could translate directly into working inventions. The specificity of these dream insights raises serious questions about whether dreams are just random brain noise. Recent research tracking people's problem-solving abilities shows a 34% improvement in performance after nights with vivid, memorable dreams compared to nights with minimal dream recall. Participants were given complex puzzles and creative challenges before sleep, and those who experienced intense dream activity consistently performed better on the same problems the next day. This improvement wasn't just about being more rested. People who slept the same amount but had less vivid dreams didn't show the same cognitive boost. Here's where things get really strange. If dreams are just random electrical noise from your brain sorting through memories, how could this chaos consistently generate useful solutions to real problems? Random activity shouldn't produce coherent insights that translate into practical applications. Yet the evidence keeps piling up that dreams regularly combine information in ways that conscious thinking struggles to achieve. Your sleeping brain appears to be doing something that your awake brain finds difficult or impossible. The mechanism behind this creative problem-solving remains one of the biggest mysteries in neuroscience. During REM sleep, your brain creates connections between completely unrelated pieces of information stored in different memory networks. The visual cortex might connect with mathematical reasoning areas, or emotional processing centers might link up with logical analysis regions. These cross-connections rarely happen during waking consciousness because your conscious mind tends to think in more linear, organized patterns. Dreams excel at combining unrelated information in novel ways that conscious thought typically avoids. Your awake brain tends to keep different types of information in separate categories. Work problems stay with work knowledge, personal experiences stay with emotional memories, and factual information stays with logical reasoning. But during dreams, these boundaries break down completely. Your brain starts making connections across normally separate domains of knowledge. This boundary breaking appears to be key to dream creativity. When your brain combines visual memories with abstract concepts or links emotional experiences with technical knowledge, it can generate insights that wouldn't occur through normal analytical thinking. The snake biting its tail wasn't a random image for Kekule. His dream brain connected his chemical knowledge with a visual metaphor that revealed the circular structure of benzene. This type of cross-domain connection is exactly what dreams seem designed to facilitate. The default mode network plays a crucial role in this creative dream processing. This network includes brain regions like the medial prefrontal cortex and posterior cingulate cortex that become active during internally focused thinking and self-referential thought. During dreams, the default mode network shows patterns of activity that are completely different from waking consciousness. Instead of the organized, sequential activation you see during conscious problem solving, dream activity in these regions appears more chaotic and interconnected. But here's a paradox that's driving researchers crazy. The activation synthesis model suggests that dreams result from your forebrain trying to make sense of random activity from primitive brain areas like the brainstem. According to this theory, your cortex receives random electrical signals and creates coherent stories to explain the noise. This should produce meaningless narratives with no practical value. Yet people consistently report breakthrough insights and creative solutions from their dreams. The tension between randomness and creativity has reached a breaking point with recent research findings. Brain scans during REM sleep show highly organized patterns of neural activity that don't look random at all. Different brain regions coordinate their activity in sophisticated ways that require precise timing and complex information sharing. This level of neural coordination typically indicates purposeful processing, not random noise interpretation. The byproduct theorists argue that even organized brain activity during dreams is still just memory consolidation that happens to produce occasional useful connections by accident. They point out that most dreams don't contain breakthrough insights or creative solutions. For every Kekule or Tesla, there are millions of people who dream about everyday scenarios that provide no practical benefits. The creative breakthroughs might just be statistical outliers in an otherwise random process. But the consistency of creative dream insights suggests something more systematic is happening. Studies show that people who work intensively on specific problems are more likely to dream about related topics and more likely to wake up with solutions. This isn't random coincidence. The brain appears to continue working on problems during sleep using different processing methods than conscious thought. The dreams that produce breakthroughs often occur after the person has been consciously struggling with the problem for extended periods. The relationship between dream vividness and problem-solving improvement creates another puzzle for the randomness theory. If dreams were just byproducts of memory processing, There should be no correlation between dream intensity and cognitive performance, but recent data shows a clear relationship. More vivid dreams correlate with better next-day performance on creative tasks, mathematical problems, and complex reasoning challenges. This suggests that the brain is actively investing more resources in dreams that serve problem-solving functions. How could random byproduct brain activity consistently produce valuable insights across different types of problems in different individuals? The mathematical odds of random neural firing regularly generating useful solutions seem impossibly low. Random processes occasionally produce meaningful patterns, but they don't consistently improve human cognitive performance. The systematic nature of dream-based problem-solving suggests that something other than randomness is driving the process. Brain scans reveal that creative dreamers have unique neural connectivity patterns that distinguish them from people who rarely experience breakthrough dreams. These patterns involve increased communication between brain regions that normally operate independently during waking consciousness. The visual processing areas show stronger connections to abstract reasoning centers. Emotional processing regions link more extensively with logical analysis networks. These connectivity patterns suggest that some brains are better equipped to make the cross-domain connections that lead to creative insights. The neural connectivity findings provide the strongest evidence, yet that dream creativity isn't random accident. People with certain brain wiring patterns consistently show better dream-based problem-solving abilities. Their brains appear to be optimized for the type of boundary-crossing thought that generates breakthrough insights during sleep. This suggests that creative dreaming might be a specific cognitive skill that varies between individuals based on their neural architecture. What makes this even more intriguing is how these same patterns of information processing are starting to show up in completely different types of systems. The way human brains combine unrelated information during dreams bears striking similarities to how certain artificial systems process data during their own downtime periods. The AI consciousness connection. Tech companies are investing billions to understand whether artificial intelligence needs something equivalent to human dreaming. The patterns emerging from AI research labs look eerily similar to what happens in your brain during REM sleep. Machine learning algorithms don't just shut off when they're not actively learning. They continue processing data in ways that mirror how your brain consolidates memories and generates new connections during dreams. This parallel between artificial and biological information processing has AI researchers asking uncomfortable questions about the nature of consciousness itself. Machine learning systems use processes that bear striking resemblances to human dream consolidation. During training periods, these algorithms take existing data and recombine it in novel ways through techniques called data augmentation. They create variations and combinations of information that weren't present in the original dataset, much like how your brain combines unrelated memories during dreams to create new scenarios. The artificial systems generate synthetic examples by mixing and matching different elements from their training data, producing outputs that are coherent but didn't exist in reality. The similarities go deeper than just recombination techniques. AI systems process information during what researchers call downtime periods, when they're not actively engaged in specific tasks. During these phases, the algorithms continue working through data patterns and making connections between different information clusters. This background processing allows the systems to discover relationships and generate insights that weren't apparent during active learning phases. The process looks remarkably similar to how your brain continues working on problems during sleep, often producing solutions that conscious thought couldn't achieve. AI researchers have become fascinated with human dreaming because it might hold the key to understanding consciousness itself. If consciousness emerges from specific types of information processing, then the mechanisms behind dreams could provide a roadmap for creating conscious artificial systems. The way your brain generates novel experiences during dreams while maintaining narrative coherence suggests sophisticated computational processes that current AI systems lack. Understanding these processes could bridge the gap between current machine learning and genuine artificial consciousness. Research on artificial neural networks that simulate dreamlike states has produced results that challenge assumptions about both dreams and consciousness. These experimental systems employ processing methods that mirror the associative and imaginative aspects of human dreaming. Instead of following linear problem-solving approaches, they generate multiple potential solutions simultaneously and explore connections between seemingly unrelated concepts. The artificial dreamlike processing creates outputs that show genuine creativity rather than just sophisticated pattern matching. These findings raise profound questions about what dreams reveal regarding the fundamental nature of consciousness. If artificial systems can achieve improved performance through dreamlike processing, it suggests that dreams aren't just biological accidents but essential components of intelligent information processing. The ability to generate novel connections between disparate pieces of information might be a crucial feature of consciousness that both biological and artificial systems require for sophisticated cognitive performance. Current AI systems process information during downtime in ways that parallel human sleep patterns, but with important differences. During active learning phases, these systems focus on specific tasks and datasets with clear objectives and measurable outcomes. During downtime processing, they explore more open-ended connections and generate variations without specific goals. This shift from directed to exploratory processing mirrors the difference between focused waking consciousness and the more associative thinking that characterizes dreams. The implications for understanding machine consciousness are staggering. If consciousness requires the ability to generate novel experiences and make unexpected connections between different types of information, then dreamlike processing might be a prerequisite for genuine artificial consciousness. Current AI systems excel at pattern recognition and optimization within defined parameters, but they struggle with the type of creative leaps that characterize human consciousness. Dreamlike processing could be the missing component that transforms sophisticated pattern matching into genuine understanding and creativity. This creates a fundamental mystery about whether consciousness requires dream-like processing capabilities. If dreams are essential to intelligence rather than just biological quirks, then the development of conscious AI systems depends on successfully simulating dream states. The question becomes whether artificial systems can achieve genuine consciousness without the ability to generate their own equivalent of dreams. The answer could determine whether we're building increasingly sophisticated tools or taking steps toward creating genuinely conscious artificial beings. The research suggests that dreamlike processing might be necessary for the type of flexible creative thinking that defines consciousness. Human consciousness involves the ability to imagine scenarios that never happened, combine concepts in novel ways, and generate insights that transcend direct experience. These capabilities emerge most clearly during dreams, when the brain creates elaborate scenarios from fragmentary inputs. If consciousness depends on this generative capacity, then artificial systems would need similar capabilities to achieve genuine consciousness rather than just intelligent behavior. What makes this particularly intriguing is how it reframes the entire AI development landscape. Instead of focusing solely on processing power and data optimization, researchers might need to develop systems capable of something resembling artificial dreaming. This would require creating algorithms that can operate in multiple modes, shifting between focused problem solving and open-ended exploration. The systems would need to generate novel combinations of information without specific objectives, much like how dreams combine memories and experiences in unexpected ways. Studies have demonstrated that AI systems incorporating dreamlike processing perform significantly better on creative tasks compared to conventional algorithms. These enhanced systems show improved abilities in generating original artistic content, developing novel solutions to complex problems, and making connections between disparate fields of knowledge. The creative performance improvements aren't marginal. They represent substantial advances in the types of tasks that have traditionally required human creativity and insight. The creative advantages suggest that dreamlike processing provides computational benefits that extend beyond simple data organization. The artificial systems with dreamlike capabilities generate outputs that show genuine novelty rather than just sophisticated recombination of existing patterns. They create content that demonstrates understanding of abstract concepts and the ability to apply knowledge in contexts that weren't part of their original training. This type of flexible application of knowledge closely resembles human creative thinking. These developments force us to reconsider fundamental assumptions about both artificial intelligence and human consciousness. If dreamlike processing is essential for creativity and flexible thinking, then dreams might represent a core feature of intelligence rather than a biological accident. The artificial systems that incorporate these processes achieve capabilities that pure optimization algorithms cannot match, suggesting that consciousness might require the ability to explore possibilities beyond immediate practical applications. The research has revealed that successful dream-like AI processing requires sophisticated coordination between different processing networks, similar to how human dreams involve coordination between multiple brain regions. The artificial systems must balance exploration with coherence, generating novel combinations while maintaining functional relationships between different information types. This level of coordination suggests that dreamlike processing is computationally demanding and requires careful engineering to implement effectively. The implications extend beyond just improving AI performance to fundamental questions about the nature of intelligence and consciousness. If both biological and artificial systems benefit from dreamlike processing, it suggests that this type of open-ended exploration might be a universal feature of advanced intelligence. The ability to generate novel experiences and make unexpected connections could represent a crucial threshold that separates sophisticated information processing from genuine consciousness. But all these theories about AI consciousness and dreamlike processing depend on one critical assumption, that we actually understand what's happening in the human brain during dreams. Recent technological breakthroughs are finally giving us the tools to peer directly into the dreaming mind. The neuroimaging to see exactly how this mysterious process Scientists can now watch your dreams unfold in real time using breakthrough brain scan technology developed in 2025. These advanced neuroimaging systems don't just detect that you're dreaming. They can actually decode what you're dreaming about while it's happening. Researchers can observe the specific neural patterns that correspond to different dream scenarios, from flying through the air to being chased by unknown figures. This technology represents the most significant advancement in dream research since the discovery of REM sleep itself. The new brain scanning techniques reveal layers of complexity in dream processing that researchers never imagined existed. When you dream about walking through a forest, your visual cortex activates the same neural pathways it would use if you were actually seeing trees in sunlight. When you dream about having a conversation, your language processing centers fire in patterns nearly identical to real speech comprehension. Your brain isn't just creating vague impressions during dreams. It's generating detailed sensory experiences that activate the same neural machinery used for perceiving the real world. Different types of dreams create distinct signatures across your brain's neural networks. When researchers examine lucid dreams, where people become aware they're dreaming, they discovered specific patterns that set these experiences apart from regular dreams. Lucid dreaming shows reduced beta band power in right parietal regions, particularly in areas like the temporoparietal junction. This reduction in beta activity corresponds with the dreamer's ability to recognize the dream state and potentially control the dream narrative. The moment someone becomes lucid in their dream creates a measurable change in brain activity that researchers can detect in real time. During the eye movement signals that mark the onset of lucidity, gamma-1 band power increases significantly in right temporal occipital areas. This gamma activity spike represents the brain's transition from passive dream experience to active dream awareness. The precision of this neural change suggests that lucid dreaming involves sophisticated brain mechanisms rather than random chance. Functional connectivity analyses reveal how different brain regions coordinate during various dream states. During lucid dreaming, alpha band coherence increases between cortical regions compared to regular REM sleep. This enhanced connectivity allows different parts of the brain to communicate more effectively, which might explain how lucid dreamers can maintain awareness and control within their dreams. The brain essentially creates new communication pathways that don't exist during normal dreaming or waking consciousness. The discovery of dream-specific brainwave patterns has revolutionized our understanding of sleep consciousness. Each frequency band serves different functions during dreams, from the high-frequency gamma waves that accompany vivid imagery to the alpha waves that facilitate communication between brain regions. These patterns aren't random fluctuations. They represent organized neural activity that coordinates different aspects of dream experience with remarkable precision. The sophistication of neural coordination during dreams resembles a complex orchestra where dozens of brain regions must work together in perfect harmony. Your visual cortex processes dream imagery, while your emotional centers generate appropriate feelings for the dream scenario. Your memory systems provide the raw material for dream content, while your motor planning areas prepare movements that your paralysis system prevents from occurring. All these processes happen simultaneously with split-second timing that requires extraordinary neural coordination. Emotional dreams activate neural pathways differently than neutral dreams. When you experience fear in a dream, your amygdala responds as if the threat were real, triggering stress responses throughout your body. When you feel joy in a dream, your reward processing centers release the same neurotransmitters they would during actual pleasant experiences. This emotional authenticity suggests that dreams aren't just visual hallucinations, but complete sensory and emotional experiences that engage multiple brain systems. Creative dreams show their own unique neural signatures that distinguish them from other dream types. When people dream about solving problems or generating new ideas, their brains display increased connectivity between regions that normally operate independently. The visual processing areas connect more extensively with abstract reasoning centers, while emotional processing regions link up with logical analysis networks. This cross-connectivity creates the perfect conditions for generating novel insights and creative solutions. The precision of dream-related brain activity challenges every assumption about random neural firing during sleep. When you dream about specific activities like driving a car or playing piano, the corresponding motor planning areas in your brain activate in precise sequences that match the actual movements required for these activities. Your brain isn't randomly generating movement patterns. It's creating detailed motor programs that would actually work if your muscles weren't paralyzed during REM sleep. Spatial navigation dreams activate the same neural networks used for real-world navigation, including the hippocampus and associated memory structures. When you dream about walking through familiar places, your brain recreates the spatial maps it uses during actual navigation. When you dream about exploring new locations, your brain generates novel spatial representations that follow the same organizational principles as real spatial memories. This suggests that dreams serve as practice sessions for spatial cognition and navigation skills. The temporal coordination required for complex dreams rivals anything the brain accomplishes during waking consciousness. Multiple brain networks must activate and deactivate in precise sequences to create coherent dream narratives. Visual processing must coordinate with memory retrieval, emotional responses must align with narrative content, and motor planning must synchronize with paralysis systems. This level of coordination requires sophisticated neural orchestration that goes far beyond random activity. Different sleep stages show distinct patterns of neural coordination, with REM sleep displaying the most complex coordination patterns of all. The brain activity during vivid dreams involves more extensive communication between distant brain regions than most waking activities. This widespread coordination suggests that dreams require more neural resources and more sophisticated processing than many conscious tasks. The dreaming brain operates more like a highly coordinated symphony than a collection of randomly firing neurons. Each brain region contributes specific elements to the overall dream experience while maintaining precise timing with other regions. The visual cortex provides imagery, the auditory cortex adds sounds, emotional centers contribute feelings, and memory systems supply content. All of these elements must work together seamlessly to create coherent dream experiences. Brain scans consistently show that dreaming involves more complex neural coordination than most waking thought processes. The number of brain regions active simultaneously during vivid dreams exceeds what researchers observe during complex problem-solving tasks or creative thinking exercises. This suggests that dreams represent some of the most sophisticated information processing that the human brain performs. The precision and complexity of dream-related neural activity make it increasingly difficult to dismiss dreams as random byproducts of brain maintenance. The evidence points toward dreams serving important functions that require sophisticated neural coordination and significant biological investment. But this raises an unsettling question about what happens when this intricate system breaks down. The sleep disorder clues. Sleep disorders strip away the mystery and show exactly what happens when dream systems fail. People with REM sleep behavior disorder lose the muscle paralysis that normally occurs during REM sleep, which means they physically act out their dreams with sometimes violent consequences. But the physical acting out is just a visible symptom of a much deeper problem. When the brainstem areas responsible for regulating REM sleep break down, it affects the entire dream processing system. People with RBD don't just move during their dreams. They often experience changes in dream content, emotional regulation, and cognitive performance that indicate widespread disruption of dream-related brain functions. The cognitive consequences of REM sleep disruption extend far beyond what researchers initially expected. People who experience chronic interference with their REM sleep show measurable declines in memory consolidation, creative problem-solving, and emotional processing within just a few months. Their brains struggle to integrate new information with existing knowledge, leading to difficulties with learning and adaptation. The memory problems aren't just about forgetting specific details. These individuals show impaired ability to form the types of associative memories that allow flexible thinking and creative insight. Sleep apnea provides another revealing example of how dream disruption affects mental functioning. When breathing lapses occur during REM sleep, people automatically shift to lighter sleep stages to resume normal breathing. This protective mechanism saves their lives but destroys their dream architecture. People with sleep apnea spend significantly less time in REM sleep and experience fragmented dream periods that prevent normal dream processing. The result is excessive daytime sleepiness that goes beyond simple fatigue. These individuals show cognitive impairments that suggest their brains aren't getting the processing benefits that dreams normally provide. Approximately 70 million adults in the United States suffer from sleep disorders that interfere with normal REM sleep patterns. This represents a significant portion of the population whose brains aren't receiving the full benefits of dream processing. The CDC has declared insufficient sleep a public health problem, but the focus has primarily been on sleep duration rather than sleep quality and dream function. The hidden epidemic of dream disruption might be contributing to cognitive and emotional problems on a scale that society hasn't fully recognized. The mental health impacts of dream deprivation create a concerning picture of widespread psychological vulnerability. People with chronic sleep disorders show higher rates of depression, anxiety, and cognitive decline compared to those with normal sleep patterns. But the relationship between sleep disorders and mental health isn't just about being tired. Dream disruption appears to interfere with the emotional processing and memory consolidation functions that dreams normally serve. Without adequate dream processing, people struggle to integrate emotional experiences and develop appropriate responses to stress and challenges. Antidepressant medications that suppress REM sleep provide an unintentional natural experiment in dream deprivation. Many commonly prescribed antidepressants reduce REM sleep duration and intensity as a side effect of their mechanism of action. While these medications can effectively treat depression symptoms, they also interfere with the dream processes that might be important for emotional regulation and cognitive functioning. Some patients report that their creativity and problem-solving abilities decline while taking REM-suppressing medications, even though their mood symptoms improve. The connection between dream quality and psychological well-being becomes clearer when examining people with nightmare disorders. These individuals experience regular distressing dreams during REM sleep that can be triggered by stress, trauma, or other frightening experiences. The emotional intensity of frequent nightmares creates a feedback loop where sleep becomes associated with anxiety and fear. People with nightmare disorders often develop sleep avoidance behaviors that further disrupt their REM sleep patterns, creating additional cognitive and emotional problems beyond the original nightmare symptoms. Narcolepsy reveals another piece of the dream dysfunction puzzle through its effects on REM sleep regulation. People with narcolepsy experience disrupted REM sleep patterns and episodes where they enter REM sleep directly from wakefulness. This creates dream-like hallucinations during wake periods and fragmented dream experiences during sleep. The loss of orexin neurons in the hypothalamus that causes narcolepsy disrupts the normal boundaries between waking and dreaming consciousness. People with narcolepsy often struggle with memory consolidation and emotional regulation problems that suggest their disrupted REM sleep patterns prevent normal dream processing. Current approaches to mental health treatment might be missing a crucial component by not adequately considering dream function and sleep quality. Many psychological interventions focus on conscious thought patterns and behaviors while ignoring the role that dreams play in emotional processing and memory consolidation. If dream disruption contributes to mental health problems, then treatments that don't address sleep and dream quality might be incomplete. The connection between dream dysfunction and psychological well-being suggests that mental health professionals should pay much more attention to their patients' sleep patterns and dream experiences. The research reveals that people with chronic dream disruption show measurable cognitive decline within months of developing sleep disorders. These changes aren't subtle shifts that only appear after years of poor sleep. The cognitive impacts of dream deprivation develop quickly and affect multiple aspects of mental functioning. Memory formation becomes less efficient. Creative problem-solving abilities decline, and emotional regulation becomes more difficult. The speed at which these changes occur suggests that dreams serve such critical functions that their disruption creates immediate cognitive consequences. The evidence from sleep disorders creates a compelling case that dreams are far more important than random byproducts of brain activity. If dreams were just meaningless noise, then losing them shouldn't cause such dramatic cognitive and emotional problems. The fact that dream disruption consistently leads to measurable mental health consequences suggests that dreams serve essential functions that conscious thought processes cannot replace. Sleep disorders provide natural experiments that reveal what happens when dream systems fail, and the results consistently point toward dreams playing critical roles in cognitive and emotional functioning. The 70 million adults with sleep disorders represent a massive population whose brains aren't receiving the full benefits of dream processing, potentially creating cascading effects that impact productivity, emotional well-being, and overall quality of life across society. But these devastating consequences of dream loss only make the central mystery more puzzling. If dreams are so critical that losing them causes immediate cognitive decline, why did evolution create such a vulnerable and expensive system in the first place? The evolutionary endgame. Evolution rarely preserves processes that burn massive amounts of energy without delivering proportional survival benefits. Yet dreaming persists across mammalian species despite consuming more metabolic resources than complex problem solving during wakefulness. The survival advantages must be extraordinary to justify such biological investment, but identifying those advantages requires understanding what early human environments actually demanded from cognitive systems. Our ancestors navigated environments where split-second threat recognition meant the difference between survival and death. They needed to read subtle social cues in complex hierarchies where misinterpretation could lead to violence or exile. They required rapid problem-solving abilities using limited resources under extreme time pressure. Most critically, they had to coordinate with others during high-stress situations where communication failures proved fatal. These cognitive demands went far beyond simple memory storage or pattern recognition. The threat simulation theory provides the most compelling evolutionary framework for understanding dream function. Research consistently shows that fear and anxiety dominate dream content across all cultures and time periods. This isn't coincidence or a reflection of modern stressors. The prevalence of threatening scenarios suggests our brains specifically evolved to rehearse responses to dangerous situations. Early humans who mentally practiced threat responses during sleep gained decisive advantages when facing actual dangers while awake. Dream content reveals this evolutionary heritage through universal themes that appear regardless of cultural background. People dream about being chased by predators, falling from heights, losing social status, failing to find resources, and being abandoned by their groups. These scenarios directly correspond to survival challenges that determine reproductive success throughout human evolutionary history. The consistency of these themes across cultures indicates they're hardwired into human psychology rather than learned from experience. Comparative research across mammalian species reveals the unique sophistication of human dreaming. Most mammals experience REM sleep, but dream complexity varies dramatically between species. Prey animals like rabbits show REM patterns suggesting escape response rehearsal. Predator species like cats appear to dream about hunting strategies. Social mammals like primates demonstrate dream patterns related to social coordination. But humans are unique in combining multiple challenge types within single dreams, reflecting the complex cognitive demands our ancestors faced as highly social tool-using beings. The energy expenditure of dreaming makes evolutionary sense when viewed as cognitive performance investment. Physical training requires energy to improve strength and endurance. Similarly, dream processing demands metabolic resources to maintain and enhance cognitive abilities. The brain's willingness to spend energy on dreaming indicates that cognitive benefits significantly outweigh metabolic costs from an evolutionary perspective. Dreams serve multiple survival-related functions beyond simple threat rehearsal. They consolidate memories of important experiences, generate creative solutions to ongoing problems, process emotional information from social interactions, and maintain cognitive flexibility under changing circumstances. This multifunctional approach suggests dreams evolved as comprehensive cognitive maintenance systems rather than single-purpose adaptations. The generative capacity of dreams provided crucial evolutionary advantages by preparing people for novel situations. Rather than simply replaying past experiences, dreams combine elements from different memories to create scenarios that might be encountered in the future. This allows development of responses to situations never actually experienced, providing significant advantages when facing unfamiliar challenges. Early humans who could mentally rehearse responses to novel threats or opportunities were better equipped to handle survival's unpredictable nature. Social dreaming aspects were particularly important for early human survival. Dreams often involve complex social interactions requiring intention reading, relationship management, and group activity coordination. These social cognitive skills were crucial for survival in highly cooperative early human societies. People who better navigated social dynamics through dream practice were more successful at maintaining group membership, forming alliances, and coordinating collective activities like hunting and defense. Creative problem solving through dreams provided another evolutionary advantage by generating novel solutions to recurring challenges. Early humans faced constantly changing environmental conditions requiring adaptive responses. Dreams combining information from different domains could generate insights unavailable through linear conscious thinking. This creative capacity proved particularly valuable for developing new tools, finding alternative food sources, or discovering solutions to environmental challenges. Emotional processing functions serve evolutionary purposes by helping maintain psychological stability under chronic survival stress. Early human life involved constant exposure to threats, social conflicts, and resource scarcity that could overwhelm cognitive systems. Dreams provided mechanisms for processing emotional experiences and developing appropriate responses without immediate real-world pressure. The sophisticated neural coordination required for dreaming suggests this process represents one of evolution's most advanced information processing achievements. The brain's ability to coordinate multiple regions simultaneously while generating coherent narratives from fragmentary inputs demonstrates computational capabilities that exceed most conscious cognitive tasks. This level of biological investment indicates dreams serve functions critical enough to justify their complexity and energy costs. Dreams might represent evolution's solution to the consciousness survival paradox. Consciousness provides tremendous advantages for flexible thinking and problem solving, but creates vulnerabilities through overthinking, anxiety, and cognitive inflexibility. Dreams could have evolved as mechanisms maintaining consciousness benefits while providing regular opportunities for cognitive reset and enhancement. This explains why dreams involve sophisticated neural coordination while producing content that seems disconnected from immediate practical concerns. The metabolic profile of dreaming reveals a system optimized for cognitive enhancement rather than energy conservation. The brain burns glucose at rates exceeding complex problem solving while generating experiences that activate the same neural pathways used for real-world perception. This suggests dreams aren't just memory filing systems, but active cognitive training programs that maintain and improve mental performance. Understanding dreams as evolutionary cognitive enhancement systems could revolutionize our comprehension of human intelligence. If dreams provided the decisive advantages that separated our species from other hominids, then dream functions might reveal fundamental insights about what makes human cognition unique. The evidence suggests we're dealing with biological processes far more sophisticated than previously imagined, processes that might hold keys to understanding consciousness itself. The evidence from 2025 research reveals something that fundamentally changes our understanding of human cognition. Dreams aren't random brain noise or simple memory filing systems. They're consciousness calibration systems that fine-tune how your brain processes reality. Your dreaming brain runs diagnostic tests and software updates on your consciousness every single night. This explains why dream disruption causes such rapid cognitive decline and why people with vivid dreams show better problem-solving abilities. We might be witnessing the birth of a completely new understanding of what mind actually is. If dreams calibrate consciousness, then the implications for human potential and artificial intelligence development could reshape everything we thought we knew about thinking itself.